Okay, so we can get started. So, hey guys, and today we're going to be talking about greedy algorithms in our last general lecture of the semester. Okay, um, so you guys are probably somewhat familiar with greedy algorithms, but basically the idea is you have some process that's going to take some number of steps, and you want to achieve like the best outcome at the end of these steps for some definition of best. Right? You want to like optimize something, like maximize it, minimize it, whatever. Um, and then in a greedy algorithm, what you do is you sort of only look one step forward and you make the best choice you can right now without thinking about what happens in the future. Um, and so then once you come up with this algorithm, the hard part is showing whether or not it works in like the general case. Um, So greedy algorithms are generally much easier to come up with than something like DP, um, but not necessarily correct all the time, um, as we'll see in some of these examples. Okay. So first, we're going to do a few examples of greedy solutions and like when they work, when they don't, using this sort of general class of problems, which is known as knapsack problems. Um, okay, so for the first one, um, you have a backpack with capacity C grams, and you have n powders where each one has value vi per gram, and in total there's wi grams in stock. And you want to fit the most total value into your backpack, where you can take any real amount of any of the powders. So you can sort of break them up into arbitrary fractions or whatever, which is why this is called the fractional knapsack. Um, so do you guys have ideas on a potential solution for this? If you have any questions about the statement or anything, feel free to ask. So if you want to do sort of like a, I guess, greedy solution that sort of makes sense here, like what would be like one of the most natural things you could do?
You want to take like the most valuable powder per 1 gram and keep maximizing that. And
Yeah,
then after you finish taking that, you get the next best value per gram.
exactly. Um, so what we can do here is look at the powder with the highest value, and then take that until either we run out of that powder or the backpack is full. And then while the backpack is not full, we keep repeating with like the next biggest value, right? So because we can do like this fractional stuff, if we have any amount of a powder and we sort of replace it with the same amount of like a more valuable powder, then that's strictly better. So we always want to use the highest value powders that we can. So that this is actually um, kind of an example of something we're going to talk about later called the exchange argument, where like if you think about um, the solution that this produces versus an optimal solution, we can sort of show that this will be always at least as good as the optimal solution by doing like a series of replacements essentially. But we'll get more into the exchange argument later. Okay. All right. So now we can talk about a different version, which is usually the more common version of the problem, which is O1 knapsack, where again we have a backpack with capacity C. This time we have n objects with again weights wi, value vi, and we want the max value that you can fit into the backpack again. But the difference here is instead of powders where we can take any fractional amount we want, we have like n distinct objects here. So you can't take fractional amounts. You can only take like 0 or 1 of each item. And so given what we just saw on the last problem, um, kind of a natural thing to think about is what if we just take the item with the biggest value at every step, or the biggest value per weight at every step, right? Because really what this value was in the last problem, it's not the value of the powder, it's the value per weight here, right? So what if we try to do something kind of like that here? Um, so you take the object that has the biggest VI over WI value, and then we sort of iterate down descending like that. Um, do you guys see what the problem could be with that? Now that we have this discrete version?
Give me a monkey dance. Oh wait, you're not brave
So,
enough to.
like, to see the problem with it, like, see if you can, like, think of an example that would break this. Like, not necessarily numbers, but like in general, what kind of case would you not want to always take the one with the biggest uh, value per weight?
You can have like a really value per weight, but like that particular weight could be bigger than your book bag, right? So you can't use this item.
Yeah, so sort of along those lines. So you can have something that's like very valuable per weight, but if you take that, um, it's sort of big enough that you can't really fit anything else in. So for example, if we have something like this case, where we have 3 items and a capacity of 10, and these are our weights and values. So if you look at value per weight, this first one here is going to have a ratio of 1, because 6 over 6. And then these two will have a ratio of like 0.8. So this one will be the most valuable per weight. But if we try to fit it into the knapsack, now all of a sudden we don't have room for anything else, because it's just big enough that we can't fit either of these guys in. But we can alternatively take these other 2 guys and completely fill up the knapsack, even though it's less value per weight. In terms of total value, it's more because we're filling more of the space. So yeah, if we in this specific case, the greedy would give you an answer of 6, um, but the optimal solution would be a value of 8. Okay. So because of this, the greedy solution fails in the 0, 1 case. Because even if, again, the higher value is more efficient per unit weight, it might stop you from using all of your space. And so because of this, for this problem, you need a more complicated solution. And specifically, there's an O of NC DP solution that I think we talked about when we did the DP lectures a while back. So we can't do a greedy solution in this case. However, one thing we can do is we can do an approximation of a greedy solution in this case. So basically, an approximation algo is an algorithm that's guaranteed to get you like within some factor of optimal, or like within some like additive amount of optimal or something like that. And it turns out what we can do is, so in this case, if we have a backpack with, we're just assuming even capacity C just for simplicity here, and we have the objects with weights WI, can we always fill it strictly more than halfway? given these two things. Given that everything is at most C, so every weight would fit in if you put it in by itself. And the sum of all your weights is at least C over 2. So if we put everything in, we could fill it strictly more than halfway, but that might overflow it, right? So given these constraints, how could we solve this problem with the greedy solution? And I guess more importantly, why would the greedy solution work? What would be a oh yeah. Yes, exactly. So that's one solution where you sort of, if you have one weight that's bigger than C over 2, then you just take that by itself. Otherwise, you can keep adding up all of your weights, just like in any arbitrary order. And as soon as that sum goes over C over 2, you can stop. No, it does work. So if all of your weights are less than C over 2, or less than or equal to C over 2, put them in any arbitrary order. And then you add them in that order until you get above C over 2. Yeah, exactly. And you can't jump from less than C over 2 to more than C over 2, or to more than C. So that always works. Yeah. So another solution that's kind of along the same lines is we greedily add the biggest item we can until it doesn't fit. And we can show that this will always be at least C over 2, like strictly more than C over 2. So why this works is assume we've added at least one item so far, which we can because all our items fit inside the knapsack. So if we've currently filled the backpack to weight W, then we have two cases. So if it's bigger than C over 2, then we're done. So if sort of the cumulative sum is bigger than C over 2, then we're done. Otherwise, we know that we have at least one item that we haven't added yet, because we know that the sum of everything is bigger than C over 2. And we also know that the last item we added has weight at most W. And because we sorted these in descending order, that means the next one we're adding also has weight at most W. So when we add this new item, the new weight is going to be at most W plus W, which, because W is at most C over 2, is less than C. And then we can sort of recurse down to these two cases. So yeah, either one of these greedy solutions would work. And they sort of work the same way, because if you have any weights that are bigger than C over 2, then this algorithm will basically just terminate after one step. Because you add the first item, then you're bigger than C over 2, then you're done. And then in the other case, any ordering would work. So yeah. Okay. So now I'm going to talk about sort of a general way to figure out if a greedy solution works. And that's sort of if it always stays ahead of the optimal, like sort of at every step. So sort of going back to like the idea of a greedy algorithm, we have this objective for the solution. So now we want to sort of consider the partial objectives like at every step. Like in the previous one, you could think about it as like the weight at every step. And so what we want to show is that the greedy solution always stays better than or equal to the optimal solution at every step, and therefore at the end, it'll be better than or equal to the optimal. So yeah, this is kind of an abstract concept, but once we see a couple problems, it should make sense. So, okay, the first problem is lecture scheduling. So we have N lectures planned for the conference with start times SI and EI, and only one lecture hall available. And we want to know what's the maximum number of lectures we can hold. So what would be a greedy solution for this? Oh, and I didn't explicitly say it, but you can't have two lectures going on at the same time in the same lecture hall. So they have to be like disjoint. You want to know basically what's the maximum number of disjoint intervals? Well, so okay, yeah. So one approach would be look at what's the earliest starting lecture and sort of add that to your schedule. The earliest one that doesn't contradict any of your previous ones. And so the problem with this is you can have a situation like this, where like, let's say these are your 4 lectures, and this is like over time, right? So these are basically your time intervals. So your earliest one would be this big one here. But by taking this one, you're stopping yourself from taking these 3. So we wouldn't get the optimal solution here. Yeah. So is there like a slight modification we can do to this to make it work? It's like this is very close to the optimal solution. Yeah, exactly. So if we sort by the end point instead of the start point, then this just works out. So yeah, we pick the lecture that finishes the earliest. And sort of the idea here is for any like number of lectures X, your greedy solution is going to finish no later than any other valid sequence of X lectures, right? Because at each step, we're taking the first one we can. So after X steps, your endpoint is going to be no further along than any other endpoint of a valid sequence of X lectures. So so this point here is kind of what we were talking about with the greedy stays ahead, because for every X, you're sort of ahead of any other valid sequence. So yeah, if the greedy took X and the optimal took more than X, like let's say it took Y greater than X, then the last Y minus X lectures in the optimal all have to fit after the X lectures in the greedy, right? Because they have to start after the X lectures in the optimal, which end after the X lectures in the greedy. So they have to be after the X lectures in the greedy, which means we can sort of add those to our greedy solution and extend it, which means that this isn't really the greedy solution. So we have a contradiction. So does this make sense? This is kind of a complicated argument.
Wait, so optimal is like the real answer?
Yeah, so what we're doing is we're comparing like the greedy solution to like the best answer.
Hmm.
Like we're not like specifying how we compute it, but just like the best answer. And we're trying to contradict like y greater than x. We're trying to show that you can't have y greater than x. Because if you do have like the optimal has more than the greedy, then we can sort of add additional lectures to the greedy, which means that your greedy would not be like maximal because we would have taken those too, right?
Oh, I see. You're trying to show that the greedy, like what we have, is just as good as the actual answer.
Exactly, yeah. Which is like the same as showing that y is not greater than x. Because we note that we always have y is less than or equal to x, because y is the minimum possible value across all solutions. So given that y is less than or equal to x, and x is greater than or equal to y, then we have x equals y, basically. So again, this is also kind of similar to what we're going to talk about with the exchange argument in a bit, where like you're considering the greedy versus the optimal solution. Okay. Anything else on this? All right. Because we're thinking about like this idea of like staying ahead of the optimal, um, think about what happens to the value of AB like at every step as you do the operations. So like, what happens to the product when you decrease A by 1 versus B by 1? And like, how can we use that to figure out which one's better? Yeah, exactly. So notice that if you decrement B, then that decreases your product by A, right? Because then your product becomes A times B minus 1, which is AB minus A. And decrementing A decreases your product by B. So we want to decrease the product by as much as possible at each step. And notice that, like, sort of at any step, the maximum value you can decrease it by is the maximum value of A and B, right? Because you're decreasing it by whatever the current A or B value is, which is always going to be less than or equal to the initial A or B value. So let's say, without loss of generality, A is less than or equal to B. So then the current value of A is always less than or equal to A. By current value of A, I mean value of A after some number of operations. Let's call that like A prime. So A prime is always going to be less than or equal to A, which is less than or equal to B. And B prime is always going to be less than or equal to B. So if we're decreasing by A prime versus B prime, the best we could do at that step is to decrease by B, because we know both of those values are always less than or equal to B. So we want to basically decrease by B as much as we can, which means we want to keep decreasing A, right? Because every time we decrease A, the product goes down by B. And yeah, so your original B, like I was saying, is bigger than any other decrease you can ever have. And then the one sort of edge case for this is note that we do have to keep A greater than or equal to X, B greater than or equal to Y. So once B hits Y, then your only option is to decrease A. And that's sort of optimal from that point forward, because that's sort of like your only option at that point. Yeah. So this part is a little bit hand wavy because we haven't shown that this is strictly better than like, I guess, doing some decrements of A and some decrements of B or something. Like, we haven't really shown that this part doesn't break the greedy solution, but intuitively it sort of makes sense that you want to do these big decreases as much as possible, and then this is your only option, so you do that. Questions on this? Okay. All right. So now we're going to get into the last thing we're going to talk about today, which is the exchange argument. Okay. So basically, the idea of the exchange argument is it's a way to show that your greedy solution is optimal, and it can give you some really nice proofs for that. So basically, given the output A of a greedy algorithm and an optimal solution B, we have some idea of like a cost on these solutions, right? Because that's what we're trying to do, is like minimize or maximize a cost. So basically, to prove that the greedy algorithm is optimal, we want to show that cost A equals cost B, basically across all inputs. And we can do this by sort of performing a series of moves that like slowly convert B to A without increasing its cost. So sort of by converting B to A without increasing its cost, we can show that the cost of A is, well, so in this example, we want like the minimum cost. So by converting B to A without increasing its cost, we show that cost A is less than or equal to cost B. But B is optimal, so that gives you the minimum cost. So we also have cost B is less than or equal to cost A. So the only solution to those two things is to have cost A equals cost B. Yeah, so you get the cost B less than cost A from B being optimal, and the cost A less than cost B from basically this series of exchanges that converts B to A. So like we were talking about with the greedy stays ahead thing, this is also kind of an abstract idea. So we're going to show this with an example. So this is a problem we looked at before in the graph theory lecture, minimum spanning tree. And we gave this algorithm, but we didn't show why it works. So basically, we want to find the minimum spanning tree of a graph, which basically is you look at all the trees that connect all the vertices, and you want the minimal sum of weights on the edges. And you can kind of think of it as the minimal cost to connect all the vertices, where the cost is like the sum of your edge weights. So for this graph, the answer would be 18, because you take the sum of the weights of these red edges. And one important thing to notice, especially for doing this exchange argument proof, is that the minimum spanning tree is not necessarily unique. Because notice that we could get rid of this edge of weight 6 and add in this edge of weight 6. And we're not changing the weight of our spanning tree, and everything is still connected. So yeah, your minimum spanning trees are not unique. Okay. And the algorithm we talked about for solving this problem was Kruskal's algorithm, where we iterate through the edges in sorted order of weight. And if adding this edge adds a cycle into the current MST, we don't add it. Otherwise, we do add it to the MST. So for example, the least weight edge is this 1, and we don't have any edges in the MST, so this isn't creating a cycle. So we can add this to the MST. Then we're going to look at this edge of weight 2. We could also look at this edge of weight 2, but we can sort of choose arbitrarily between edges with the same weight. So yeah, this one also does not create a cycle. And then the next few don't create cycles. Then we get to this edge of weight 5. And notice that if we add this edge, it creates a cycle with the red edges. Right? So if we add this edge of weight 5, now all of a sudden we have this cycle here, which we can't have in a tree. So that means we don't add the edge of weight 5. So we throw that out, which is what we're denoting with the blue. So then, again, we can arbitrarily choose one of these 6 edges. So for example, we pick this one. This does not create a cycle. It's connecting 2 new components of the MST, so that's fine. But then this 6 creates this cycle here, so we don't want to add that. And then this 7 creates basically this cycle of size 5, so we don't want to add that. And then once this process is over, we have a spanning tree. So because the graph is connected, we're guaranteed that this will give a spanning tree. So now we just need to show that it's the minimum spanning tree. So before we go on, are you guys good with this? The algorithm and the problem in general?
Yeah.
All right, cool. Okay, so now we're going to get into the proof. So we have to consider sort of the greedy solution versus the optimal solution. So let S be the tree formed by Kruskal's algorithm, and T be a minimum spanning tree. Oh, whoops. And T is a minimum spanning tree. So T is our optimal solution in this case. And like we talked about at the beginning of the exchange argument, we're going to sort of convert t into s over a series of steps without increasing the sum of weights of its edges. So you're sort of slowly replacing the edges in t with edges of s without increasing your total edge weight sum. And then we can show that that means the cost of t is greater than or equal to the cost of s, which means that s also has to be optimal, like we talked about before. Okay. So if s equals t, then we're obviously done because they're the same. So that means s is clearly a minimum spanning tree because t is. Otherwise, there's an edge e that's in t and not in s, right? Because they have the same number of edges. They both have n-1 edges. So if those edges don't completely match up, then we have an edge e that's in t and not s. Okay. So for example, if this is your t, this is your minimum, and this is your s, notice these are like different trees. And this one contains the edge e, and this one doesn't. So what we do in the first step of this exchange is we add e to s. And because e is not originally an s, it's going to form a cycle. Because otherwise it wouldn't be, because otherwise we would have added it during Kruskal's, right? Because at this step where we look at edge e, if that didn't add a cycle, we would have added it in. So that means there has to be this cycle here. Also notice that there's exactly one cycle containing e in this graph because it's a tree. And if there were two cycles containing e, then we could sort of merge those. Like let's say there was a cycle going out like this or something. Then we could sort of merge these two cycles into one cycle and show that there's a cycle like within S. And we'd have to be kind of careful about that because these two cycles might overlap somewhere. Like it might loop down to this vertex or something. But regardless, we'd be able to find a cycle in S. So yeah, we have exactly one cycle containing E in this graph. Okay. So because T also does not contain cycles, because it's also a tree, then if we look on this cycle, there has to be an edge F that's not in T. So we know that E is in T. And if all of these other edges were in T, then we would have this whole cycle inside T, which is impossible. So we have an edge F, for example, this one, that's on this cycle in S, but does not appear in T. And notice that you could have multiple, right? Like we could have chosen this edge as F, but we can choose arbitrarily. Okay. So now the idea is we want to sort of exchange E and E for F in T without increasing the total weight, right? Because we have this edge is E is in T, F is not in T. So we want to sort of swap them out without increasing the weight. Because that also makes T more similar to S, right? Because S is the opposite. S contains F, but it doesn't contain E. So by swapping it, we're making T more similar to S. Okay. All right, so here's kind of the complicated step. So like we talked about before, E was not added during Kruskal's, right? Because otherwise it would have been a member of S, because S is the Kruskal's tree. So at the step where we would have added E, adding E created a cycle in the MST. Okay. So because, and by the MST, I don't mean S. I mean the pieces of S that were there at the step where we would have added E. Right? Because like let's say E was the first edge, it was like the lowest weight. Then when we added it, then that definitely would not have created a cycle because there's no other edges for it to create a cycle with. So we would have added it. But the fact that we did add it meant that there were edges there that were placed before E that formed a cycle. And again, like we talked about before, this S union with E only contains one cycle. This is the only cycle in this graph, basically. So if adding E produced a cycle with that subset of the MST, right? Because all the edges that were there in the MST at that point were there in S at the end. So if we create a cycle at that point, then that means we had to have completed this cycle. Right? So at this step where we added E in Kruskal's, we couldn't add E because all of these 4 edges had to already be there. So yeah, but the criteria for all 4 of these edges being there is that their edges had to be less than or equal to, their weights had to be less than or equal to the weight of E. So in particular, that means that the weight of F is at most the weight of E, right? Because it's on this cycle, and if the weight of F was greater than the weight of E, then F wouldn't have been there when we tried to add E, so then this cycle would not have been complete, and we would have added E to the MST. Okay. So now we have weight F is less than or equal to weight E, so if we sort of add F and subtract E, we're not increasing the weight of T, right? Because we're sort of adding a negative number to the weight, or a non-positive number to the weight. And it's going to have to be exactly 0 because we know this is minimum. But we know we're not increasing the weight. And also notice that this is guaranteed to keep it as a spanning tree, because let's say you look at T without E or F. Then that's going to be, it's going to split your graph into 2 components, right? So you have basically all of these vertices and this vertex by itself. And you know that E and F are going to connect, they both have to connect those 2 components. Because if you add sort of either one, right, because those components are the same in these 2 graphs. And you know that if you add E, that connects those components in T. And if you add F, it connects those components in S. So if you add F here, that's also going to connect those components here. That's also like a not super rigorous part. But we're more focused on, I guess, the argument about the weight than we are about this still being a spanning tree. Like it makes sense that if it splits it into the same 2 components, this edge that joins those 2 components here would join the 2 components here. Okay. So now T is sort of one step closer to being S without increasing its weight, right? So we've taken E out of T and we've added F. So now these trees are, like, in a sense, more similar. Like they have more edges in common. So we can now repeat this argument until they're equal, right? Because initially they have at most n-1 edges not in common. But we can repeat this and like at most n-1 steps until they're equal, right? Because they're still not equal at this point, right? Because this S contains this edge and T contains this edge. But after one more step, we can make them equal. So this was a very long proof. So do you guys have any questions about any part? There's a lot going on here. But again, like your basic idea is you want to sort of swap out the edges until you turn your optimal into your greedy solution and show that that never makes it get worse. Any questions on this? Okay. So that's all we had for today. So thank you guys for coming. As always, we have the slides on the Discord, and we'll have recording up soon. And we're gonna have a contest on greedy problems Wednesday at 8. So yeah, see you guys.